Hi everybody. We are solving dynamics problems. Our topic is kinetics. We are solving problems of curvilinear motion in a plane. We are solving them by directly applying Newton's second law. The title of our topic is Force, Mass, and Acceleration. A cylinder P with a mass of 0.4 kilograms is moved vertically along a slotted path with the equation R equals 0.6 theta meters, using a forked arm. Here, theta is in radians. If the cylinder's constant velocity is 2 meters per second, determine the normal forces applied to the cylinder by the rod and the slot when theta equals pi radians. Assume that at any given instant the cylinder is in contact with only one edge of the path and one edge of the fork. Yes, we have a particle whose trajectory equation is given in polar coordinates. We will examine the motion of the particle. We will find out what the force F and the force N are at a given instant. At the instant when theta equals pi radians. The equation of the trajectory is R equals 0.6 theta. What kind of motion is this? Its trajectory lies in the vertical plane. So, what we see here as a side view is curvilinear motion, and its velocity is constant. What does it mean for the velocity to be constant in curvilinear motion? It doesn't mean the vector is constant. Of course, it means its magnitude is constant. Because for a vector to be constant, both its direction and magnitude must be constant. In curvilinear motion, it's impossible for the vector's direction to be constant. Because if the trajectory is curvilinear, its direction always changes. Or at least it changes during the curvilinear part. When we say curvilinear motion, it doesn't necessarily mean that every part of it will be curvilinear. As you know, some parts can be rectilinear. Yes, the entire trajectory of this motion is curvilinear. Therefore, the direction of velocity is always changing, but its magnitude remains the same. It's stated that its magnitude doesn't change. Now let's draw the free body diagram. At the instant when theta equals pi radians, the forked arm is in a horizontal position. Therefore, the gravitational force is perpendicular to the forked arm. It is perpendicular to the axis of the forked arm. It is vertical and downward. At the same time, the force exerted by the forked arm on the cylinder is also vertical. The force F is also vertical. But we don't know if it's upward or downward. We can represent it randomly. For now, let's assume that it is upwards. The direction of this will become clear as a result of our calculation. Let's call the force exerted by the slotted path N. It is perpendicular to the tangent of the slotted path. It is perpendicular to the tangent of the trajectory. Let's assume it is in the direction shown in the figure. Let's show it as in the figure. Again, its direction will become clear as a result of our calculation. Will it be to the right or to the left? Will it be towards the concave side of the trajectory or towards the outside? This is how a free body diagram looks. Now let's show the axes of the polar coordinates. The equation of the trajectory of this particle is given in polar coordinates. Therefore, it is obvious that we will solve this problem using polar coordinates. We know the r-axis. It always passes through the pole and the position of the particle. So which side is positive side? The side where the theta angle is measured is positive. Therefore, it is positive to the left. The r-axis is positive in the direction shown in the figure. It is positive to the left. The theta axis is positive in the direction of the increase of the theta angle. It is perpendicular to the r-axis. That is, it is positive downwards as shown in the figure. It is vertical. The r-axis is horizontal, the theta axis is vertical. Polar coordinates are as follows. We know the values of r and theta at a given instant. We consider theta to be pi radians. So if we substitute pi for theta, we get r equals 0.6 pi meters. The r coordinate is equal to 0.6 pi meters. Now let's show the accelerations. Let's show the two perpendicular components separately. Instead of showing the total acceleration, let's resolve it in two perpendicular components and show its components. Let's show components in polar coordinates. As you know, acceleration is always towards the concave side of the trajectory. It cannot be outwards. I'm showing the components here inwards as well. I'm showing them towards the concave side of the path. The calculation we'll do later will show whether these were chosen in the right or wrong direction. We assume AR is in the negative direction and A theta is in the positive direction. Let's choose them accordingly. Now let's start applying Newton's second law. Let's apply it on the r-axis first. Total Fr equals MAR. There is only one force, N, that has projection onto the r-axis. The projections of the other two forces are zero. Therefore, we have a chance to find force N directly from this equation. Let's write it down. We see that the weight and the force F applied by the fork arm are perpendicular to the r-axis. Their projections are zero. Only the projection of the force N exists. This is found by multiplying it by the sinus of the angle shown in the figure. N sinus psi. Let's call that angle psi. Let's call the angle between the r-axis and the tangential axis psi. Then the projection of N is equal to N sinus psi. However, we see that it is in the negative direction. We put a minus sign in front of it. The opposite side is MAR. Now we will find the force N from here. But first, we need to find a few things. We will find the angle psi and the r component of the acceleration. After finding those, we will find the force N. Now let's find the angle. What angle was this? The angle between the r-axis and the tangential axis. We know that the velocity vector is always tangent to the trajectory. It coincides with the tangential axis. Therefore, the angle that the velocity vector makes with the r-axis is the same angle, psi. Let's write the tangent of this angle. The tangent psi equals the opposite leg divided by the adjacent leg. In terms of velocity components, v theta over vr. Now, to find psi from here, we need to find v theta and vr. Let's recall what they are equal to. V theta is our theta dot, and Vr is r dot. Let's write these expressions out. That is, let's write the derivatives with respect to time. Let's substitute d theta divided by dt instead of theta dot, and dr divided by dt instead of r dot. Then, if we perform the necessary operations, simplify, and rearrange, we get tangent psi equals r divided by dr over d theta. We will find psi from here. We know r, but we need to find the derivative of dr over d theta. Let's find that now. Let's find the derivative of r with respect to theta. We have the function. It is given. R equals 0.6 theta. The equation giving the variation of r with respect to theta is given. If we take the derivative with respect to theta, we can easily find the derivative of r with respect to theta, which is 0.6. dr over d theta is equal to 0.6. R is equal to 0.6 pi. Substituting these, the 0.6's cancel out each other, leaving pi. We get the tangent psi equals pi. The angle whose tangent is equal to pi is 72.34 degrees. Yes, we found the angle. Now let's look at the acceleration component, AR. We know that AR is equal to r2 dot minus r theta dot squared. There are some unknowns here. If we find them, we will have found AR. What do we need to find? We need to find the r2 dot and the theta dot. Let's find the theta dot first. To find the theta dot, we consider the velocity vector again. We know that v squared equals vr squared plus v theta squared. The square of the velocity vector is equal to the sum of the squares of the perpendicular components. We will find the theta dot from this. Now, we are given what v is. It is 2 meters per second, and it is constant, the magnitude of the velocity. We already know that vr is equal to r dot, and v theta is equal to our theta dot. We saw this earlier. Let's substitute these values. 2 squared equals r dot squared plus our theta dot in parentheses squared. We will find theta dot from this. But first, we need to find r dot and substitute it. We find r dot from the r function theta relation. We find r dot by taking the derivative once with respect to time in the relation r equals 0.6 theta. R dot is equal to 0.6 theta dot. Now, the only unknown is theta dot. We isolate theta dot from this. We find theta dot equals 1.011 radians per second. We have found theta dot. Now, it's time to find our 2 dot. To find the r2 dot, let's take the derivative with respect to time both sides of the equation we just obtained. Since the left side is constant, its derivative is 0. The derivative of 2 squared is 0. Let's take the derivative of the right side. If we take the derivative there, we get the following equation. Of course, we need to know how to take derivatives here. Our subject is dynamics, not mathematics. You should be able to take these derivatives or integrals. Yes, we obtained this equation. Now we will find the r2 dot from here, but first there are some things we need to find. We already found the r dot, 0.6 theta dot. We got theta 2 dot. Now something new. We find theta 2 dot as follows. If we take the derivative twice in the theta relation of the function r, we get our 2 dot equals 0.6 theta 2 dot. If we isolate theta 2 dot from there, we obtain theta 2 dot in terms of our 2 dot. There is nothing unknown anymore. If we substitute the values here, if we write our 2 dot divided by 0.6 instead of theta 2 dot, if we write 0.6 pi instead of r, and if we substitute 0.6 theta dot instead of r dot, we obtain the following equation. In this equation, we know the theta dot. The only unknown is the r2 dot. From this, we find the r2 dot. We get r2 dot equals minus 0.177 meters per square second. Yes, now we can find AR. AR equals minus 2.104 meters per square second. So AR is in the direction shown in the figure. We already thought it was in the negative direction. We were correct. It turned out to be in the direction we chose. AR equals minus 2.104 meters per square second. Now there is nothing unknown. From this, we find the normal force, the force N. We find N equals 0.883 newtons. Now, to find the other normal force, the normal force applied by the forked arm, that is, to find force F, let's write Newton's second law on the theta axis. Total F theta equals ma theta. We project the forces onto the theta axis. We equate them to ma theta. The gravitational force and force F are already on the theta axis. Their projections are equal to themselves, but one is in the positive direction and the other in the negative direction. The gravitational force is in the positive direction of the theta axis. Force F is in the negative direction. Therefore, W minus F. The projection of the normal force N is N cosine psi, which is in the positive direction. W minus F plus N cosine psi equals ma theta. From this, we will find F, but first we need to find a theta. We know the weight because the mass is given. We have found the force N and angle psi. Only a theta is unknown. So, let's find a theta. We know that a theta can be found from the relation r theta 2 dot plus 2 r dot theta dot. We know it is equal to this. To find a theta, we first need to find theta 2 dot and r dot. We previously found that theta 2 dot is equal to r2 dot divided by 0.6. We found a relationship between the theta 2 dot and the r2 dot. We found the r2 dot. We know this. Therefore, we can find the theta 2 dot from here. We also know that the r2 dot is 0.6 theta 2 dot. From the relation r equals 0.6 theta, r is the function of theta, we can easily obtain these equations. There is nothing unknown here. Now we substitute the known values. We find a theta. A theta equals 0.670 meters per square second. We see that a theta is positive, that is, in the direction shown in the figure. So we guessed that correctly as well. The direction of a theta is also as shown in the figure. It is in the positive direction. Now we can substitute the known values and find F. We can find the force F. We find F equals 3.924 newtons. That's it. Goodbye.